Okay, we're live. And I think I fixed my microphone problem on the last stream. My microphone was at 50% volume, and that's probably why people were saying the game audio was too loud. But so today, what we're going to do is we're going to be doing a little bit of a different kind of stream. Today, what I'm going to be talking about is overclocking on Zen 4 and AM5, the tools that are available to do that, as well as why you would want to do that, or why it's probably not really worth it in the long run for a 24/7 system. And we're going to talk about reasons of why you want to overclock, why not, and is it worth it or not. So I guess what I'll do is, since I'm using Paint here to illustrate this, so essentially we'll talk about two things, and then I guess we'll do some viewer Q&A toward the end in terms of what we can do. So today we're going to be talking about two different methods to overclock, because essentially that's kind of what it is. There's two different methods to overclock AM5 processors. One being the built-in PBO, or the performance boost overdrive. So this is kind of the evolution. I think it's now in its second or third iteration from the days of Zen 2 and X570. So a lot of the methods have carried over. Now the silicon is a little bit different. Obviously we're on a different kind of node from TSMC. So the silicon process is different. The way things on the actual die are placed have changed in terms of positions relative to where they are. Now you still have the I/O die, but in the end there's really two methods, one being PBO and the other one is known as OC mode, which is more of like a manual overclock. We'll go so far as to say legacy method. So this one we can we won't spend too much time talking about this, because honestly, what I remember from overclocking in the days of Zen 1, this is essentially how I used to overclock processors before Zen. So think like FX8350, Phenom, Phenom 2, those sort of things, like the old AMD. So AMD before the days of Ryzen was the way you used to do things. And if we're talking about Intel, so we'll talk about Intel just briefly, because as far as I know, I haven't really dabbled too much in overclocking on Intel in recent history, although what I remember is that the overclocking methods on Intel are a lot more basic, so they're a lot more like doing it on OC mode, but there are a little bit of there's more granularity there with what you can do, although you have pretty much granular control, full manual control over the AMD processor when you're in OC mode. But the only thing with OC mode is it does lock you out, or it does disable a lot of the power saving features. Like I think it turns off C states, and it's kind of not really necessary. So we're probably not going to talk too much about OC mode. It's just kind of there, but it's not really used much anymore unless you're just kind of testing things out. What I remember in Zen 1 days was that the minute you went and put like either a manual offset, like a positive or negative voltage offset, the early BIOSes on like X370, it would consider that OC mode, and it would turn off all the XFR and the PBO and all that stuff. So in the end, a lot of the overclocking has to be done using PBO, and that's because you do kind of want to get the benefit of the lower idle power states, the lower C states. The efficiency gains with Zen 4 really kind of only really make PBO the realistic method for overclocking. Now, we'll also talk about undervolting briefly. So a lot of people have left comments on my channel talking about undervolting. They've asked about undervolt, curve optimizer, that sort of thing. So let's kind of dive into it. We'll address undervolting, because undervolting essentially is kind of the reverse of overclocking. So because typically with overclocking, when you're trying to drive a higher frequency, you become voltage limited relatively quick. Now again, it depends on the silicon. So again, there's a variance there. So the silicon lottery determines whether or not you can hit certain clocks at specific voltage levels. But most of the time when you're overclocking, you become voltage limited, so you have to add more voltage. You don't want to reduce the voltage, you want to add more voltage. So when people always ask me about undervolting, and undervolting is the opposite of overclocking. So if you're going to undervolt, you're essentially dialing back the power or the voltage available to the processor. So at that point, you're trying to really stretch. You're trying to get clock stretch, and which is a term that AMD uses internally when it comes to overclocking on the processor. But essentially, with undervolting, you're trying to see what is the limit in the silicon. What can you actually do? How high can the clock go using less voltage, which translates into less power, less heat, less fan noise, etc. All that kind of stuff applies here when you're doing undervolting. But it's a form of overclock, but I don't want to call it overclocking because it's not really overclocking. It's really going in the opposite direction. So let's kind of dive into the theory here. Let's cover the fundamentals. So essentially, this processor. So I'm just gonna what I'll do is let's just draw out a. What I want to do is draw a rectangle to represent like the processor. So in the processor, we have two CCDs. We'll call them CCD 0 and CCD 1. I think most people who are familiar with Zen processors kind of already know about this. And then you have an I/O die, which in the case of Zen 4, these two top dies here, these are on TSMC 5 nanometer, and then the I/O die is on 6 nanometer. So they're able to get a lot of efficiency in terms of the process node by using two different technologies. So 6 nanometer is it's easier to manufacture, it's a little bit more mature, it's older, it's not as high-end, so to speak. So they're able to save costs on their I/O die. So this chiplet architecture is something that has been around since the days of Zen 2. And in reality, it's kind of an evolution of what AMD already had with their interposer technology that they developed back when they were working on the R9 Fury. So if anybody in the chat or anyone watching this stream remembers the R9 Fury and the R9 Fury X graphics cards from AMD back in 2015, those used HBM, so the first generation of HBM, and essentially the way those were designed is there was if you think of the die up here, I'm just going to draw it out. So it had the GPU die in the middle, and then around it they had 4 blocks of HBM memory. Each were 1 gigabyte of HBM memory. So essentially you had 4 gigabytes. But what's interesting about this design was the interposer, which is kind of like a fabric. It's like a substrate fabric that links the memory to the GPU die. So this was kind of the first generation of that sort of chiplet-like technology. And then they, further enhanced it with Vega 2 or Vega, and then there was Vega 2, which was Radeon 7. And then at that time, they were already introducing it with Zen 2 back in 2019. So Zen 2 was the first edition of this chiplet-style architecture on the CPU side of things. And I do want to reference a video. So Gamers Nexus did do an excellent interview. I forget the VP of engineering at AMD, but he was the guy, when he was an engineer working on the Fury, basically the interposer and the high HBM on the GPU. He was on the Radeon side, and they moved over to the CPU side and started pioneering the chiplet design, the fundamental chiplet design on the CPU side. And I think that's really worked out for them in terms of allowing them to scale real well with these updated versions, because next year we're going to see the X3D on AM5, so the Zen 4 X3D, which is going to be really, really interesting. I think that one's going to probably be a single CCD, much like the 5800 X3D that's available now, but it's going to be on the newer node, to the 5 nanometer with the cache stacked on top of it. So I don't think that overclocking, now we are talking about overclocking on this video, but I don't think that those 3D chips are going to be overclockable, nor would you really need to do that, because essentially the cache is already so close. It's literally like physically stacked on top of the CCD, so it's kind of like a skyscraper if you look at it planar. So, you know, that's going to run really, really hot, and everything's in such close proximity. So you really don't want to be overclocking that if you care about longevity. So I don't really see the need to do that. And the thing is, the cache is so fast that that's why you get this massive boost in gaming performance. So let's kind of pivot here back to what we were talking about with the overclocking. So essentially, you have the two CCDs, and in those CCDs, you have 8 cores each. Now I want to try to, like, well, that's not going to work. So I guess I have to just draw it out. So you have 8. Well, you guys get the idea. There's essentially 8 CPUs, or 8 cores, not CPUs. There's 8 cores inside each of these upper rectangles here. So those are your CCDs. So if you have a 7950X or a 7900X, you have 2 CCDs. You have both of them. If you have a 7700X or a 7600X, you have a single CCD. Although I have heard, I mean, I think DeBauer had delidded a 7600X and found that it did have a dummy die. There was a dead I/O die next to it. And I think they do that because of, I guess it's less waste. They don't have to throw it away. They just kind of put it there for stability, so that additional support under the IHS does actually make the distribution, the weight distribution, or the pressure distribution on the actual processor dies more equal, as opposed to having only a single CCD, and then you have like this empty space over here where there's nothing, essentially. So I understand why they do that. It makes sense to me, because they did the same thing with the EPIC processors, or the first gen Threadripper and the second gen Threadripper had the same thing. If you had anything less than the 32 or 24 core, you did have the dummy dies on there as well. But for PBO, it kind of breaks down to, let's go ahead and erase this section up here. We don't need this anymore. So you have a reference clock, you have a clock generator, which is an external, we'll say CLK for clock. This is a 40 megahertz clock signal that is on the motherboard, so this can apply a timing signal. So the thing with overclocking that I think is often overlooked is that the timing of how everything works, all the different components have to all be in sync. Now you can unsync certain things, but when we talk about asynchronous, it doesn't mean that we're decoupling everything and allowing things to run at different speeds or different clocks relative to each other. What that means is typically it applies to memory. So it typically means that if you're running in asynchronous mode as opposed to synchronous mode, it means that instead of sending a command to memory once every clock cycle, it means you will send one command every 2 clock cycles. So it's essentially half as opposed to every single clock cycle. So if you guys have looked at overclocking memory, or if you've been looking at running the Expo profile memory, or you're just just trying to manually tune timings, or if you just have an XMP memory kit like myself and you're just running that with a Ryzen CPU, you may have noticed that there is something in the BIOS called, I think it's called it's M clock. So there's M clock, there's U clock, and there's F clock. These are the 3 different clocks that apply to memory. So essentially, let me I probably have to erase this thing because this is kind of in the way. So unfortunately, that's gonna have to go. So let me just we may have to draw out this a little bit. So let's just label some stuff here. So we have the clock generator. Let me move that down. We'll put that over here. And then we have those clocks. There's more than just those clocks. So we have the CG-PLL. So we have a phase lock loop, the clock generator. So this is the clock generator phase lock loop. So this is going to go here. I'll just put that right there. because that is going to apply or supply the different PLLs. So you have the C clock PLL, you have the SoC PLL, I believe, and I think there's more than one of these. I don't know if the motherboard exposes all of them. Of course, you have the USB PLL. So the thing is, if you're messing with the external clock generator, typically you don't have to do that, or you really don't want to do that, because that can throw off the timing for things like your storage, your USB ports, all that kind of stuff. You start having a lot of weird problems if you do that. But what this is illustrating here is that you essentially have the clock to the clock generator PLL, and then that is going to supply various different clocks to these other entities. So the C clock is important because that's the one that will, this one will influence something called VCO, which we may talk a little bit about, and we'll kind of label these out. But VCO will then apply the clock for your CCD. So the CCD or the CCX PLL. So that's, and then this goes to your cores. So this is the clock for the PLLs. So you have your multiplier, so it's going to determine whether you're going to be doing like 5 gigahertz, 5.5 gigahertz, 5.8 gigahertz, 6 gigahertz, etc. So I think, what do we want to say about SoC? So SoC is the system on a chip PLL. This used to be things like, if you go further back in time, you know, this was essentially the north bridge of a motherboard. If we're talking like way back, like AM2, I think AM2 had a north bridge, if I'm not mistaken. Maybe it didn't. I can't remember. I know like Socket 939 had one, but then it all got integrated into the processor, so that just became known as an SoC. But essentially, you might see certain motherboards might label this as NB. NB meaning north bridge, and they might have some kind of like voltage. I don't know if they'll say VOC, but it's like north bridge underscore voltage or something like that. So you just gotta have to watch out for it. So it does help to understand the terminology, the various ways that these things can be named. You know, because like I think Intel, if we're overclocking on Intel, like it's the same thing. There's like the VCC, SA. There's like a bunch of them for DDR5 too, but we're not going to talk too much about that. So SoC PLL, USB PLL. Now I do want to focus a little bit on SoC because this is the one that is for the memory, if I remember correctly. So this one will actually provide not just memory because it's the SoC. So the SoC, system on a chip, this is the component that talks to the chipset. So your Promontory 21 chip, if you're on a B650 motherboard or B650E, or your dual, like your primary and your secondary Prom 21 chipsets, if you're on X670 or X670E. So this one has, I think, like 3 or 4 different ones. If I remember correctly, you have the PCIe PLL. So that one has its own PLL. Then there's going to be one for the F clock, so the fabric PLL. You have all these phase lock loops, and right now what we're talking about, for those that are not really following what's going on, we're talking about how the clock signal keeps everything in sync. So this is going to be either multiplied or divided depending on what is the reference signal supposed to run at. So typically these clock signals on these different phase lock loops are going to be 100 megahertz reference signals. So you also have the unified memory controller PLL, and these are all like clock phase lock loops. I'm just kind of shrinking down the name. And then you have the onboard graphics has its own PLL because this is new to Zen 4. All the Zen 4 chips have a integrated graphics component now. So this used to not be here. If you're talking like Zen 3 and Zen 2, you had PCIe, PLL, F-Clock, and UMC, and now you have an additional graphics PLL here. And all of those derive their clock from the SoC PLL. So let me just kind of draw this like that. Okay, so USB, I believe, I don't really need to spend too much time on that one. But effectively, this is like 100 megahertz reference signal or reference clock for all of these. Except I think USB might be something different. I think USB might be, it might literally take the raw 48 megahertz. I don't really remember, but this one might just be running at the raw 48, whereas these have a multiplier value, some decimal number to get them to 100, if that makes sense. So hopefully people are not completely lost, but this is kind of the background, the foundational info that I do want to kind of put out there for those that are curious about how, like, what are all the different underlying layer 1 parameters that exist at the actual CPU and the SoC level, and why the timing matters. Why is the clock important? Well, it does. It's really important, actually. It's probably one of the most important things. So that's kind of why we're illustrating it here. So you have the UMC, the F clock, the P clock. So now I think what we want to talk about is memory, because I do think that probably the most performance you can get beyond stock is typically going to be from memory. Although, unfortunately, the IMC, at least my experience with AMD so far, with these first generation Zen 4 processors, is they're really not that great when it comes to memory. Now, it's better than first gen DDR5 on Intel, so it's better than Alder Lake. But, you know, compared to 13th gen like Raptor Lake, in terms of what you can actually get out of max DDR5 speeds, Raptor Lake is definitely superior when it comes to memory overclocking. It's just the first generation thing versus a second generation thing. So Intel was first to the game with DDR5. Now, granted, when they launched Alder Lake with the DDR5 motherboards last year, those motherboards were very expensive, and the DDR itself was very, very expensive. So AMD's kind of running into the same wall of issues that Intel had to deal with last year when they started being the early adopters on DDR5. So, unfortunately, the IMC is kind of picky, or I don't want to say flaky. It's not flaky. It's just kind of the quality of the IMC for a first generation product leaves a little bit to be desired when it comes to high-speed memory. So typically, from what I have personally seen, the IMC on average, you're typically going to be able to do 2 DIMMs at 6,000 megahertz. So basically what AMD has told the press is that 6,000 megahertz or mega transfers on DDR5 is the sweet spot, because anything above that will force you to drive the, I think it's the UMC or the U clock at half. So that kind of leads us to this next point here. We have the, let me see, from the UMC, you have 2 different things here. So you have U clock, PLL, you have another phase lock loop, and then you have mem clock, PLL. So this influences your memory controller. So the U clock is for the memory controller. So this is going to be the IMC. So this is, now this is just looks like I'm typing a bunch of acronyms, but hopefully people are following what I'm referring to here. And this one is going to be the actual RAM. So this is the RAM. So this one is a CPU. This one is the actual RAM itself for these phase lock loops. F clock is different. So that one's going to go to something called the Infinity Fabric, which is a fancy marketing term for what used to be the hypertransport. We'll call this IF. Okay, so I guess, should I type these out? Infinity Fabric. And then this is integrated memory controller. And then this one is going to be physical RAM. Well, everybody knows what that is. That's just that physical memory. Or I guess non-volatile memory. Whatever. I don't want to type another acronym. So these are essentially what you get. So if we think about memory, so let's use what I have here for example. Let me just bring up CPU-Z to show you guys. We'll just illustrate it with CPU-Z. Just open CPU-Z and then I'm going to share it here on the stream. So you guys can see it. Let me add it. Or is it already in there? No, it's not in there. So how do I add CPU-Z? There we go. Can I move it around? I can move it. Let's just leave it over here. Whatever. Okay, we'll just put it right there. So you guys can see there's my... So this is the CPU that we're using. So this is an AMD... Hey, Joel. Yeah, I thought I would do something different because people have been asking about overclocking. Hey, Joey. I'm doing the video that you and a couple of others have asked me about to look at overclocking on Zen 4. So we're doing that. So I just kind of been talking about the fundamental approaches when it comes to overclocking, and now we're kind of first going to talk about memory, and then we'll talk about the actual CPU. We're going to go into things like PBO, curve optimizer, the power limiting, and what that can do from a performance standpoint and an efficiency standpoint. So I have here a AMD Ryzen 9 7950X, and the thing that you'll notice is, well, it's 16 core. You can see it's 5 nanometer. It says 5 nanometer. Now, what I wonder is, does the chipset say if it's 6 nanometer? No, it doesn't. Okay, but it is though. So the IO die, which makes sense because it's not part of the main board. So, but you guys can see, it's interesting how my mouse shows up in 2 spots, but that's because I'm sharing CPU-Z separately. Yeah, we're just going to go over overclocking fundamentals for those that are curious. And I'm also going to talk about like workarounds for some of the teething issues that have been afflicting some early adopters when it comes to things like PCIe compatibility. And people have asked about post times. I've already done a video on how to speed up the post time or the boot time on Ryzen or on Zen 4 specifically, but people have still asked me. So we'll talk a little bit about that. Essentially, there's a setting you have to turn on in the BIOS called Memory Context Restore, which basically tells the motherboard the next time the PC has to cold boot, or even warm reboot. So be cold start or warm start. Basically, it will skip the memory training. Now, a lot of people say that that's not a good thing. I disagree with them because if your computer has already been 100% stable, there's no reason for you to have to retrain the memory every cold boot or every warm reboot. So I turned on Memory Context Restore and I've left it like that since day one. I've never had any problems. Do you know if the TSMC 5 nanometer that RDNA 3 is based off of is the same node as the 40 series 4 nanometer? No, well it's not. It's not, right? Because the RTX 40 series is on the 4 nanometer process. So the really good thing for TSMC by doing this, by having all these different nodes, these high-end, state-of-the-art manufacturing nodes going simultaneously, is it does allow them to scale up their production. Because if everybody was all on 5 nanometer, or if everybody was on 4 nanometer, it's 5 nanometer that's called 4 nanometer. I don't know about that, because I do think that the RTX 40 series is on a different one. Because I know that the Zen 4 is the 5 nanometer process. I could be wrong though. I haven't actually read up too much on TSMC's nodes specifically, but from what I know, I do think that they're different nodes. I think NVIDIA is on the most advanced node, AMD is on the second most advanced node, but AMD has purchased more capacity. Because AMD, basically, the way I understand it is the RDNA 3 and Zen 4 are being made on the exact same node, and then the IO dies are being made. So the IO die for Zen 4, which is 6 nanometer, that's the same node that the what do they call those? The MCMs, the memory chip or the multi-chip module on the RDNA 3. I think those are also 6 nanometer. So I think those are all the same. Basically, AMD is using 2 different nodes from TSMC. They're using 5 nanometer and 6 nanometer. Then NVIDIA's using the 4 nanometer one for the 40 series. But the 4 nanometer one is more expensive. So NVIDIA is paying top dollar for that 4 nanometer node. That's my understanding of it. I could be wrong. I don't know if the 5 and the 4 are the same. I would assume that they're different though, because I don't think TSMC doesn't strike me as the type of company that would advertise like they wouldn't say one number, but then in reality it's a different number. Intel, on the other hand, is completely okay with calling a 10 nanometer node Intel 7. So, but I don't think TSMC is that type of company. So you guys can see here, so this is the processor, and then you can see on the memory, actually if we look at this, the core speed you can see is right now, it fluctuates around, so when it's, what we're streaming with this processor, so it's mostly going to be around 5.5 gigahertz, but it's typically going to drop occasionally to like 4.6 or something, and then it'll go a little bit boosting on 1 or 2 cores to the 5.8, but you won't really see that here because this is kind of showing an average number. Samsung called a 10 nanometer node 8 for the 30 series. Yeah, but it's all kind of relative to something else. I feel like they're always comparing. It always depends on how they're measuring the distance of something on the transistor. I always forget, but like Intel measures it one way, TSMC measures it another way, and then Samsung measures it in a different way. So it all kind of breaks down, or it all kinds of falls apart. So, one of them will say 10, one of them will say 8, one of them will say 7, even though it's 10. One of them will say 8, even though it's 10 or whatever. Like the way I understood Samsung, in my mind, was the 8 nanometer node for like the 3090. I don't really know in reality what it actually was, but it's one of those deals where Samsung says 8 nanometer, but that might be equivalent to, like, basically the way that they're saying it is if Samsung says 8 nanometer, if you measure it using TSMC scale, it might only be a 10 nanometer node, or it might be equivalent to a TSMC 10 nanometer node. That's the way I understand it. So I think because TSMC is manufacturing both the 4 nanometer and the 5 nanometer, I think it's 2 different nodes. But I haven't really done much research into that, so I don't really know. So the core speed here is derived from the number here. This one is going to be what essentially gives you that 5.5 number that we're seeing. Then if we look at the memory, you guys notice we have 2 numbers here in CPU-Z. So there's the DRAM frequency, and then there's also the uncore frequency. So the DRAM frequency is going to be based off of this, I believe. And then the uncore frequency that's listed here is going to be based off of this right here, the U-clock phase lock loop, or the IMC, depending on what the BIOS calls it. Some BIOSes will call it U-clock. I think most of them call it U-clock. Some might actually say like SOC something, PLL, or F-clock, U-clock something. U-clock equals half F-clock or something like that. So essentially, let's kind of talk about the different, so synchronous and asynchronous mode. So when we run synchronous mode, the easiest way for me to illustrate this is to just kind of draw out a clock signal. So this is one. How should I illustrate this? So it's here, it rises, it falls, and then it goes back, and then it'll repeat. So this is essentially one clock cycle. Oh, you guys can't see it because CPU-Z is in the way. Let me fix that. Move it over here. So this is, well, here, let me do another rising edge. So this is We'll just draw it out like this, so this makes sense. So think of it like a clock pulse. So where there's a square, that's essentially a 1. So if I were to label this, this would be, this is a 0, this is a 1, this is a 0, this is a 1, this is a 0, and then it'll just repeat, right, over and over again. It's like binary. So it's on or off. It's like a switch. On 1, off 0, on 1, off 0. So this is like the clock signal. You can think this is basically repeating indefinitely over and over and over again. So when we are running the memory in what's known as synchronous mode, or when you're running your UMC, the Unified Memory Controller, and that also refers to, like I said earlier, so if we're talking about the Unified Memory Controller, and that refers to both the U clock and the mem clock. So the U clock is the IMC clock. So that's in the CPU. That's in the Ryzen CPU. The mem clock is telling the RAM what the actual memory that you install, whether it's Corsair Vengeance or Dominator or G-Skill, Flare X, or G-Skill, what was the other one? Trident Neo, or whatever you use, T-Force Vulcan, whatever. There's like so many different ones. That's going to be telling it what to run at from the mem clock PLL. So when we run in synchronous mode, that means that I want to send a command from the CPU to memory, or I want to do a command, I want to do some kind of work every clock cycle. So I can't remember if it executes on the rising edge, so that means this edge, or if it's on the falling edge. We'll just say the rising edge. So when it rises, it does something. So meaning every clock cycle. So if we call this one cycle, this is another cycle, and then there's like a third one over there as it repeats. So if I do one command every cycle, that means right here on the rising edge, I have one command. And then right here on this next rising edge, I have another command. So that means I have two commands, or one command per clock cycle. That is synchronous mode, and that is the mode that you get when you're running uclock equals memclock. So when you have it in the BIOS, if you're tuning the memory and you set uclock equals memclock, that means every clock cycle, it will do a command. So it's a 1-to-1 ratio. It's a synchronous ratio. So the way you can verify in Windows, or in the operating system, with CPU-Z at least, the way you can verify that you're running in 1-to-1 synchronous mode is by looking at the uncore frequency and comparing that to the DRAM frequency. If those two numbers are equal, so you can see they're basically the same number, that means that you're running in synchronous mode. So it's basically what we've illustrated here. Every clock cycle, there will be a command. This is on DDR5, but this is kind of like 1T. This is like 1T if you're thinking of like DDR4 terminology. So that's effectively 1T with DDR4, but this is the same sort of deal. They call it synchronous mode for DDR5. So your uncore, or I guess your IMC, and your DRAM run at the same clock. Now remember remember it's double data rate. So the reason why people are probably looking at this and it's like, well, why is this only 2600? Well, you multiply it double to get the actual number, right? So that would equate to 5200 megahertz. So I'm running RAM right now at 5200 megahertz. That's the actual rated speed on the memory. We're running 64 gigabytes at 5200 megahertz. But remember, the 5200 megahertz is the double data rate number, DDR number. So the actual frequency is going to be half of that. So that's why it's showing 2600 here in CPU-Z. So the other mode is asynchronous mode. Asynchronous mode means it's basically it says uclock, or is it, yeah, uclock equals half of memclock. So I guess what I'll do is I'll type out the equation. So there's synchronous mode, which is U clock equals mem clock. So that's synchronous mode. And then you have asynchronous mode, which is U clock equals 1/2 of mem clock. So it's basically mem clock divided by 2. We'll just say mem clock divided by 2. So that's asynchronous mode. So what that looks like is instead of 1 command per clock cycle, it means 1 command every other clock cycle. So that means for 2 clock cycles, so for 2 clock cycles, I will execute 1 command to memory. Or I'll send one command to memory every other clock cycle. So meaning this 1 command could be on the falling edge. It'll probably be on the falling edge of the first clock cycle, or however it does it. I don't know the full details of how it actually sends that command, but effectively you get 1 command every other clock cycle. So if this executes on the first clock cycle, it means the second clock cycle won't actually do anywhere, or there won't be anything that's sent down there. There's no transmission there. So why is that useful? Why is that actually a thing? So the reason why asynchronous mode exists is because it's very hard to run the memory, the IMC, or the integrated memory control in the CPU at much higher frequencies compared to the RAM. So the RAM can clock to whatever the Samsung B die, Samsung A die, Hynix die, whatever it is, even Micron, whatever that's able to clock up to, the IMC in the CPU might not be able to do the same speed. And that's the reason why AMD has advertised the Expo profile 6000 megahertz as basically the sweet spot. That's kind of because in reality, that's the upper limit of what you can get on these first generation IMCs. Have I gotten back to testing Intel Arc? Not yet. Not yet. What I'm probably going to do is I'm probably going to put it in the main system that we're using here and do content on it that way. I have some ideas for it, but I'm thinking more along the lines of a video talking about like the budget options for the holiday season and why Arc is actually a good value right now. From that one stream where we were looking at Black Friday deals, like the Arc GPU made a lot of sense compared to a lot of what we saw. There was kind of a lack of options from NVIDIA. There were a lot of options from AMD, but I do want to kind of point out that Arc is a good one. Yeah, okay. Yeah, no, I saw your post in the Discord. I have one small form factor case, but it's not like super small. So I might do a video on that, but I don't really have something that's what I consider true small form factor. You got the small form factor, the H1. Yeah, I saw your post. Yeah, and you're gonna pair that up with the Intel CPU, so you can test the what do they call that, hyper-encode. That'll be interesting to see if they can test the hyper-encode. I was thinking of doing that. The only problem with me, if I throw that back in my 13th gen system, it's always kind of a pain to swap back to a different GPU, because I just don't like having to DDU everything all the time. It's just very annoying. Yeah, if you can, definitely because it's small form factor, definitely get something that's low wattage. You don't really want like a super high wattage system or a high wattage CPU for something like that. But the reason why this exists is because if you guys are trying to overclock memory, or if you're trying to push high frequency RAM, the IMC is going to be the limiting factor. In my experience with both Intel and AMD, the IMC has always been the limiting factor when it comes to memory overclocking. Almost never have I been limited by the actual RAM itself. Now, granted, that's because I'm buying RAM that I know is either the right type of die. So in the case of what I'm using, I have Hynix memory in here right now. But I do also have Samsung memory that Micro Center gave me for free when I purchased the Zen processor. But I haven't really tried the Samsung memory. But the Hynix memory right now on DDR5, Hynix is really your go-to if you're looking for like anything that's 6,000 or above. That would be all Hynix. There are some Samsung. I think we talked about it in a previous stream, but the way you can tell, like, the way you can kind of guess if something is Samsung is if the numbers are like this. Like if it's like 36, 36, 36, 89. If it's SK Hynix, it's usually something like this. You know, it'll have the cast latency. The CL number will usually be something different than the two middle numbers. Whereas with Samsung, usually, very, very high probability, not guaranteed 100%, but usually Samsung's memory timings on DDR5, the first three primary timings are always the same number. And Hynix always has like a better number, like a lower number for their first number, and then everything else kind of falls in line with what you see on the Samsung. So that's my own experience. So I know like Buildzoid did a video talking about this exact same topic. And he also was pretty good. I watched that video. I was listening to him. He was pretty good with guessing which one's which. But I know for a fact, because the memory that I'm running, you guys can see it here on the stream. This is 36, 89. This is Hynix memory. You guys can see it right there. SK Hynix for G-Skill. So that's Hynix. Now, if I were to pop in my, or swap out to my Samsung memory, the Samsung memory that I got for free from Micro Center was the 36, 36, 36, 89. So both of them had the same advertised frequency, but the sub timings were different. So the Samsung was the 36, 36, 36, and the Hynix was the 30, 36, 36. So Buildzoid was spot on with his basically going over like different DDR5 DIMMs. So yeah, it's pretty accurate there. So, but again, like why asynchronous mode exists, it's there so that you can hit higher frequencies on the memory. Because if you decouple them, like for example, I can run if I'm running let's just use 64. Let's just use 6,000 as an example. So if I'm running 6,000 mega transfers on my DDR5, that means my mem clock PLL is going to be 3,000 megahertz or 3 gigahertz, and that means if I'm running asynchronous mode, the U clock is running at half of that. So the U clock is only going to be at 1,500 megahertz. So it's much slower. The U clock's much slower, but the memory is so much faster that when it comes to performance, you won't really notice much of a difference. Like, even though the U clock the processor is sending one command to memory every other clock cycle, the memory's frequency is so fast that it overcomes that difference in the speed, or in the polling rate, or I guess the command rate of the memory. So another way to look at this, I guess another way to oversimplify this is, or not really oversimplify it, but another way to think of this, if you're thinking about it from DDR1, if you're looking at DDR1, what happened here? Oh. Wow, the bots found us. Okay, I think we're good. So, synchronous mode is basically 1T. Asynchronous mode is essentially 2T. You can kind of think of it that way. That's an easier way to think about it, I think. But because you typically don't see the RAM You don't really see RAM timings, DDR5 RAM timings advertised with the 1T or 2T nomenclature anymore. It's typically always going to be synchronous mode or asynchronous mode. That's usually what they're saying. But asynchronous mode is very much similar to how 2T command rate works on DDR4 and DDR3. So that's something to be aware of. Because I do think that a lot of the memory overclocking with the Zen 4, and also to another extent like Intel's processors as well, like their DDR5 processors, like 13 gen and 12 gen, are like that. So that's where a lot of the performance lies. I do think it's in memory. Unfortunately, a lot of what we're talking about with all this memory stuff is still very much early days. So your mileage may vary. It's really, you're really playing the silicon lottery when you're an early adopter to a new platform like this, and you want to run high memory. When I say high speed memory, I'm thinking like 6400 mega transfers or above. The thing is, it's a first generation processor, so you got to think of it like Zen 1. It's like Zen 1 all over again. Like the IMC on Zen 1 was pretty bad at in terms of like trying to hit anything above 2933. I still remember to this day that 2933 was your 24/7 stable memory clock. And then if you were on 2 DIMMs, you could do 3200 megahertz if you were lucky. But then again, like, you had to buy Samsung B die, and it was very, very, hit or miss with like the silicon lottery in terms of whether or not you got a good IMC or a good bin to IMC or not. So, that's kind of how it is with this new AM5 platform. However, this is still a lot better than what we had with AM4, with AM4. So, the only thing that I have noticed so far is that if you're running memory above 5200 megahertz, the only problem is sometimes your S3 sleep mode or standby mode in Windows doesn't really work properly. So, like, when you wake from sleep, the computer doesn't really recover. So it hangs at, like, I forgot what the debug code was. But the only real workaround is to not clock your memory above 5200 megahertz, which is kind of disappointing in a way, because, I mean, I was trying to run mine at 6000, and it works at 6000, but, I can't put the computer to sleep and have it reliably wake up. So I backed it down to 5600, and then it was kind of hit or miss. Sometimes it would wake up, sometimes it wouldn't wake up. So I backed it down to stock 4800 megahertz, like JDEC timing. Never had a problem with that. So I was running like JDEC, number 6 here, and that was fine. But then after that, I basically bumped it up to 5200, since that was what the official supported speed from AMD is, and then anything above 5200 on Zen 4 right now is considered an overclock, which is not supported. So it's kind of weird, because even though they say DDR5 6000 is a sweet spot, realistically 5200 is the stable 24/7, no headaches required type of setup. So that's kind of how that is right now. But that will improve with the AGESA updates. It's really going to be AGESA updates. I've talked to Gigabyte, so I have a Gigabyte Aorus Master, and they basically told me 5200 is what you want to run if you're using the computer as a workstation or like a professional setting. You don't want to be running it at 6000. So that's actually coming from the vendor. So they're telling me don't run it at 6000, run it at 5200. And I run it at 5200, and sure enough, no more issues with waking it from sleep. Everything works fine. So I'm just running it at 5200, and that's why you guys see I'm running the U-clock at 1-to-1 ratio. So I get to run it at 1T, 5200, which is the max supported official speed, and not have any problems. So still waiting on those AGESA updates, and then I'll try to overclock memory again. You're gonna order the 12400. Oh wait, once I know it will ship. Order that. Oh, I think Intel 13 gen systems will work better with DDR5. Yeah. Yeah, well, and I said this earlier, like Intel, so 13 gen is basically the second generation for DDR5 for Intel. Like Alder Lake was worse than Zen 4 from what I know. Now I never tried to I completely skipped DDR5 with 12th gen. I ran it on DDR4 and didn't have any of those problems, although I did have problems with E-cores causing stability issues with certain applications and games. But 13th gen, so far, you know, I can run my memory at the... Now, I haven't even bothered to overclock my RAM on Intel yet, but on Intel, I'm running these exact same DIMMs, these SK Hynix. You guys can see I'm running the same exact memory. When I did my unboxing video of the 13900K, I did show the RAM, so the G-Skill Ripjaws S5. That's in the Intel system, and it's also the same memory that you're looking at here that's in my AMD system. So the AMD system, it runs perfectly fine at 5600, which is what this memory is spec'd at. You can see from the part number, or even right here, max bandwidth 5600. So Intel, no problems with 5600, but that's because that is within the realm of Intel's official specification for 13th gen. If you look it up online, Alder Lake 12th gen, the maximum supported RAM speed is 4800 JDAC. Anything above that is not supported on 12th gen. So that's why it was very hit or miss. With 13th gen, it is 5600. 5600 is the official supported speed. So what I have purchased of this RAM that we're looking at here, this works perfectly fine on 13th gen out of the box because it's still within the official supported spec. It is not considered an overclock by Intel's definition. Anything above this, so like 6000, 6400, anything beyond that, that's all considered an overclock, and that is not guaranteed by Intel. It's an unsupported configuration, so your mileage may vary. Now with AMD, the maximum supported RAM on the first generation Zen 4 is 5200 megahertz. A lot of people seem to forget that. They always think that it's 6000 for some reason, and that's because all the reviewers tested it on launch day at 6000, and they all kept saying that AMD did say this, so AMD was kind of digging their own grave when they said that 6000 is a sweet spot, but you know, there's an asterisk there saying that that's an overclock, that's officially unsupported. So 5200 is the official supported speed, and that is the reason why I'm running my memory at 5200, even though it's actually capable of doing much, much higher. But I will revisit this with the next AGESA code update. So the AGESA code that I'm on currently is the 1003 A revision. So I'm still waiting for Gigabyte or AMD or whoever to get a newer one out there. Okay, so I guess we don't really need this anymore. It's taking up space on the screen. You think yeah. And Intel uses the same, basically the DDR5 terminology on Intel is a little bit different, but it's effectively the same thing. So Intel calls synchronous mode Gear 1 mode, and they call asynchronous mode Gear 2 mode. But it's effectively the same thing as, you know, uclock equals memclock, and uclock equals memclock divided by 2. Yeah. Yeah, no, it's good. It's if you can get one. You know, I was looking at the listings for Z690, and because of the Black Friday sales, I feel like most retailers have sold through their Z690 inventory. There's a whole bunch of Z790 that no one's buying because it's not worth it. So and there's no cheaper option. I think there's B660, but B660 is so heavily gimped. TSMC N4 provides a 5% boost over N5. They're both part of the same N5 family. Oh, okay. So it's N4 and N5. So N4, so is N4 not 4 nanometer then? That's confusing. Because what I've heard is N4 is 4 nanometer, but unless they're defining that in a non-standard way. All right, so let's talk about PBO now here. So we're gonna talk about the performance boost overdrive on here. What I'll do, let me try to make some space here. Let me move this up, move all of this up, scrunch this up here. Node 4. But so node 4 is 5 nanometer? 5 is not referred to. Okay. Well, that's weird. For some reason I thought I read that RTX 40 series, the node 4 is the 4 nanometer. So they're basically all 5 nanometer? Oh, okay. It's a different revision. I get it. So N4 is a newer revision over N5. You would think that the higher number means that it's a higher revision. That seems kind of weird to me. That makes it even more confusing, actually. Let me move this over here, I guess. If we still need this, we can bring it back. Kind of put that over there, I guess, or whatever. Just put it here. Okay, so it's all 5 nanometer. Okay, well then they're all kind of the same then. So PBO. So there's a couple of things here. There is the new Precision Boost Overdrive, or PBO 2. This is basically, I guess I should have put a 2 here. But there are a couple of things we need to be familiar with. A couple of terms that we need to be familiar with. So there is the sustained power limit. And that is how AMD measures TDP. It's a really weird mathematical formula. It has like a theta in it and some Greek letters. Looks like an algebraic equation. We're not going to really talk about that here, but essentially, this is the TDP. This is a sustained power limit over a longer period of time, or I guess I should say it is a long period of time. AMD will say indefinitely, but this kind of depends on the thermal solution and the power supply to a lesser extent. But most people who are building their own PC, I would think that if they're buying a PC new or building a PC new, they're probably going to get a decent power supply that's going to be very capable of running the system without any issues. So thermal design power, thermal design power is the TDP. But the way AMD defines the TDP, the way that they derive the thermal design power is their sustained power limit. So when they say, for example, 170 watts, they say that the processor should be able to, the system itself, but the processor primarily should be able to sustain a 170 watt power draw at a given frequency curve, and it'll scale with a certain amount of voltage that will make it equate to the 170 watts. So power is equal to the voltage times the current. So there's going to be an amps number in there, and then there's going to be the voltage number in there. So the V core and the way VCO, which we've kind of drawn up here, how that equates to the actual clock of the cores is another thing. There's an N4P now that's 11% faster than N5, but again, they are part of the N5 nanometer family, the 5 nanometer family. Okay. Yeah. So, let me go back here. we'll just delete it. Well, this is the stock, right? So we know that when we're talking about the Ryzen 9s, the 170 watt is typically the 7950's stock configuration. Now there is an eco mode. I've talked about this in a separate YouTube video. So that 105 eco mode, or the 105 watt TDP, that effectively makes the processor limit itself to what the AM4 processors, I keep wanting to say AM3 for some reason, but AM4 processors, because Zen 4 and AM4 is weird, but AM4, so basically the 5950X had a TDP of 105 watts, whereas the new 7950X has a TDP of 170 watts. That's the stock out-of-box configuration. So you can, a lot of people, I don't really want to draw too many comparisons to Intel, because Intel, the way Intel measures TDP is a little bit different, and they use two different power levels to define their TDP now. So it's even more confusing if you start looking at Intel stuff. But Zen kind of has a similar setup. So the 170 watt is kind of like Intel's power limit 1, but the socket on AM5 allows a total power draw, or TDP power draw, of 230 watts. So this is, you can kind of think of it like 170 watt is kind of like power limit 1 on Intel, and 230 watts is kind of like power limit 2 on Intel. But that's not exactly, it's not a valid comparison, because in reality, the power levels on Intel are vastly different in terms of how the power draw equates to or how it actually relates to the TDP versus how AMD kind of does theirs. Because AMD's is essentially the processor power that can be sustained indefinitely by both the power supply and the thermal solution. So your cooling system that you're using matters a lot with the new Zen 4 processors. So I can't stress that enough, because they say that the processor is designed to handle 95C, 24/7. TSMC's node is designed to be able to sustain that kind of operation, or those operating temperatures. So for longevity and reliability, AMD has said that this is not a problem. But I would beg to differ. I just don't like the idea of running a silicon processor at 5 degrees below boiling water. To me, that just doesn't equate as a normal thing. It just seems kind of weird. So the eco mode is a very good safe bet if you do want to run on air cooling, for example, and you don't want to deal with the 95C, even while doing a full blender run, or Cinebench runs, or overclocking. I mean, with overclocking, you're kind of not going to be power limiting yourself, but there is curve optimizer for that, which we will talk about in a little bit here. But yeah, like eco mode is definitely a thing for 24/7 operation. It effectively makes the computer, or it makes the processor, behave very similar to the 5950X, while outperforming it in every way imaginable. So there is that as an option. So the sustained power limit over the TDP. The TDP is the thermal designed power. Let me just give you guys some definitions. So this is thermal design power is the TDP. It is the way AMD comes up with a number when they're designing the number. Like in this case, they're saying 170 watts is the TDP of the 7950X. This is the power that can be sustained indefinitely by power supply. So by the PSU, we'll just say by the PSU and thermal solution, so the cooling effectively. So that is the main way that they're deriving their sustained power limit. That is a little different from Intel, because Intel operates on something called tau, which is a time value. So Intel does not allow their power limits to, or I guess their power limits can only operate within a certain amount of time, and that the motherboard will control that time limit. So meaning you can have really, really lousy cooling on Intel, and it will It will gladly run all the way up to boiling water, as I've shown in a video recently on the channel. An Intel versus AMD video. I've shown like Intel does go to 102C, I think is what I saw in that DaVinci Resolve render. And that's on an air cooler. The difference is the tau value, the time value on the motherboard will basically tell the processor to thermal throttle after a certain amount of time. So run, heat up, but then like slow down. And that tau value, that time differential value, will determine how long it can cook itself or how short it can cook itself. So that is a user provisional value, but I do think that there are probably some knobs in there that the motherboard manufacturer will put in there for reliability reasons to prevent the processor from just killing itself. But that is something that's different from AMD, where AMD defines their TDP as a sustained power limit. So it is a limit of two things. It is the power and the thermal solution. Now, we all know that the power limit is going to be 230 watts because that is the upper bound limit of the socket. That's what the AM5 socket will do. So your PSU has to be able to deliver, clean power up to 230 watts, which is relatively easy to do. For most PSUs these days, so you're really thermal limited on AMD. So the way I see it is you're thermal limited on AMD, and on Intel, you're more likely to be power limited, but in reality, as we have seen, with 13th gen at least, oftentimes you are also very much thermal limited on that processor as well. So how good do you think the small form factor 750 watt gold PSU that comes with the... it should be fine. It should be fine. I wouldn't try to put anything, I wouldn't run a graphics card that's above 300 watts in there. So, I would not run, a 6900 XT or a 3080 or above in that case. I personally wouldn't do it. Or at least not with that power supply. But, yeah, 12400F or whatever, plus, whatever 250 watt or lower TDP GPU will probably be fine. Okay, now we're going to talk about another parameter here. So this is going to be the package power tracking. So the package power tracking is the total power the CPU can draw from the socket before the boost drops off or levels off, however you want to say that. So PPT, you can think of this as kind of it's not a clock speed, it's a power amount. So it's going to be in watts or milliwatts. It's a power number. So it's the total amount of power the CPU can pull from the socket before the boost drops off. So this parameter, like we were talking about with the sustained power limit, so this number is typically supposed to be 230 watts. But again, this number, if we're talking about extreme overclocking, so if we're using a chiller, or if we're using LN2, or if we're using, some kind of exotic liquid or full custom loop, this parameter can be adjusted to try to pull more power through the socket. So this parameter is going to be very much dependent on the VRM of the motherboard. So this is where the high-end motherboards actually shine here. Your 3070 Ti might be an issue if it can draw. No, I don't think it does. The 3070 Ti is 270, 75 or something like that. 330 is the 3080. You're gonna put the A770 in it though, so it's So you'll be fine. 750 watts is enough. So the limiting factor on the PPT is usually not going to be the motherboard, but it can be. So I guess this parameter depends on the VRMs. But usually, if you're looking at a motherboard, if you're overclocking on AM5 and you're using a motherboard for either what we're talking about, Asus Crosshair or ASRock Taichi or Gigabyte Aorus, or you know, BioStar Valkyrie probably, although I don't really know how to navigate that BIOS. All of them, MSI, Meg, or even the MPG, like all of them, are they all have legitimate high-end VRMs, so that the VRM isn't really going to be the limiting factor on the PPT. So realistically, again, with the PPT number, you're probably going to be dependent or limited by the thermal solution when it comes to the actual overclocking and min-maxing the system. So this is kind of it. So I guess here thermal solution matters as well as the VRM. You won't be pulling 300 plus watts unless you're doing a stress test like FirmArk. Yeah, that's true. But but still, like even with FirmArk, right? With FirmArk, the cooling is most likely the limiting factor, not so much the VRM. Even with FirmArk, the VRM on most of these motherboards is pretty competent. So I wouldn't have an issue with any of them. Like, you know, we've looked at a lot of motherboards on this channel in the past, you know, basically since the launch of Zen 4, and with all the ones that I've looked at, really the buying decision isn't so much the VRM as it is actually more the feature set. All of them seem to have very, very robust VRMs. I mean, for the price you're paying on AM5's motherboards, I would expect them to all have very, very good VRMs. So we didn't really look too much at the VRMs, but I imagine they're all really, really good. So again, the VRM is not really going to limit us here. It's really going to be the thermal solution that matters the most. So, you know, like in my case, I'm running a Noctua NHD 15. I've been thinking about doing liquid cooling more and more because people have been asking me about it. But I don't know, you know, maybe the way I see it is I might actually revisit liquid cooling next year on the channel. I'm really waiting for the X3D CPUs to come out. So depending on what we get next year, if I can get an X3D CPU, depending on how that performs, I could turn that into my workstation computer, and then I can use what I'm using now as you know, like a overclocking bench type computer, and then I'd be okay with like putting that under liquid. So right now, because the 7950X is the main computer that I use for work and everything, I don't want to be, you know, subjecting it to a lot of like stress tests, torture tests, that kind of thing. So it's a daily driver, so I kind of have to use it as such, right? So that's kind of where I'm limited there on that. So that's going to be the PPT. And the only other, there's a third one, and we're going to talk about a couple of other things with Curve Optimizer after this. But there's the electrical design current. So that's the EDC parameter. So that one, so this is basically, so remember we talked about power. So far we've looked at power. Power is a function of voltage and current. So we haven't really talked about the current. So here's the current parameter. So the electrical design current is the maximum amount of current under transient conditions for a short, thermally insignificant time. That is the definition. So I'm going to type it out. Max peak current, or I guess we'll just say, well, we'll just say peak. The maximum peak current under transient. Now, the key word here is transient, because remember, just like with graphics cards, when we talk about transient spikes, or transient voltage spikes, or current spikes that cause OCP to trip and turn off the entire computer while gaming, we have seen this with lower quality PSUs, or not necessarily lower quality PSUs. Sometimes lower quality PSUs actually just let it slide and they don't do anything until they blow up. But sometimes there are strict PSUs that will, like for example, Seasonic. I've had a Seasonic that will turn off on me if I'm using that with like a Vega 64. So that is something to keep in mind. But going back to the CPU side, transient conditions for a short, insignificant, they use the word insignificant time. So what they mean by this is it's a very, very short duration. It's not like several seconds long. So let's just think of it this way. The amount of time, the interval of time that this EDC number can, or I guess the amount of current draw that it can pull, the maximum amount that it can spike to without causing OCP to trip. That's kind of what this number is. That's what it's associating it with. And it happens in such a short time interval that the only way to measure this would be to look at it under an oscilloscope. There's no way for you to see this. There's no way to see it like without any kind of special monitoring equipment. So that's kind of what that means. Quake 2 RTX as well will draw 310 watts on the 3070 Ti. Really? Okay, I didn't know that. Well, I know that doing ray tracing does increase the power draw on the graphics card. I didn't know it would make it run that high though. I didn't even know the 3070 Ti could use that much power. So here, the EDC is typically going to be VRM limited. So this is going to be VRM limited. Now, a lot of these high-end motherboards, they have robust enough VRM design that, you know, if you're doing an extreme overclock, if you're bringing this thing under LN2, EDC actually becomes more relevant than if you're just doing a regular overclock on liquid or even on air for that matter. So actually, personally, like my own personal experience with playing around with this CPU on air, you can't really do much with overclocking. I mean, unless you're upping the temperature limit to like 115 C, and I don't want to do that for 24/7. So look up the VBIOS of the EVGA, and you will see the power limit is 325. Oh, okay, you're talking about an AIB, so that's yeah. I was thinking like Founders Edition card, but yeah. So these are the three parameters. So the other thing too is you guys might recognize these, in parentheses at least, you might recognize these parameters from not just my video, but anytime you look up like how to enable eco mode on Ryzen. So in the early days, like in the first month of release, there was no easy button to enable eco mode on Ryzen. Now most BIOSes have the eco mode toggle, but effectively these three parameters are what the eco mode is actually changing. So out of the box, most of the high-end motherboards, and when I say high-end motherboards, I'm talking about X670E. So like the Ace from MSI, the Gigabyte Aorus Master, the Asus Crosshair Hero, the Extreme, all that stuff, the Taichi. By default, they all are essentially doing what Intel is also doing, where they're running these three parameters in unlimited power mode, because if you go and you try to tune these, as soon as you go to custom or manual, you'll see that the limits that they've set for these three parameters are so high that the processor will never use that much power. It'll never like draw that much current. They just basically max out the number, and at that point they basically limit it to what we have listed here. So it instantly makes it thermally limited or current draw limit or VRM limited. So that's the reason why we're seeing 95C as a normal environmental operating temperature on these processors. So, because if you would turn on eco mode, you won't really see 95C unless you're running this on, you know, like a Wraith Prism cooler, or, you know, something even less competent at cooling something like this. So yeah, I see the post. So Micron, yeah, they're all gonna be Micron. 325 watt limit, target is 310. Okay. So is that a dual BIOS card? Does it have like a 325 and a 310 mode? Okay, so those are the main, these are like three major parameters that influence the the boost behavior, the TDP, the PPT, and the EDC. Let's try. What do I want to talk about next here? Let me see. Just kind of going through my notes of what's the talking point for overclocking. Let's see. So there's a couple of other parameters. I don't know. Now this might vary on the BIOS. Actually, let me draw a box around this so that we just kind of keep that off to itself. So there's a couple of other things here. There's something called the Fmax. It might be listed as something else in the BIOS. It could also be HTF max. So this is the max allowed frequency at high temperature. I guess the HTF max is the high temperature frequency maximum, or I guess max frequency at high temperature. There's another one here. Proc. This is basically the hot temperature. This is basically the overheating signal, or I guess this is basically the parameter that says the CPU is overheating. This is the parameter, for those wondering, that will make the computer literally shut off. It will literally shut off. PC World actually had this happen. So they tried to use an old 2007 stock cooler from an old AM2 motherboard. They put it on their Ryzen 7000 series CPU, but the thing is they did not have the mounts correct because they were using an old mount. What is this post? Definitive guide to configuring 3rd and 4th gen Ryzen. But this, I think, if memory serves, 115C is the number. So it's like, if at any point the hotspot on the CPU hits 115C, the computer will literally turn off. So I think that's the number. If memory serves, because I know that was the same hotspot limit on the Radeon 7 and the RDNA 1, where those GPUs would severely start thermal throttling if it got to that point. So I think it's 115. This is essentially the absolute maximum temperature. Once it hits this temperature, it's game over. The thing will turn off because it's too hot. So now, if someone's going to ask about the lower limit, like the negative, like the LN2 number, that I don't know, because I've never put the CPU under LN2, so I don't know what that limit is. Now there might be some kind of there might be like a zone where usually if you're under LN2, there's a zone. I want to say it's like negative. It's like past -40 to, there's some range where sometimes it's like a black zone where the processor just doesn't really behave well. But then when you go colder than that, then all of a sudden it's fine. It's weird. I don't really know why the processors sometimes behave that way. But that is something. But in terms of lower limit, I don't really know. I don't think, as far as I know, I don't think there is a lower limit. It's just the computer might just behave strangely at certain extremely low temperature ranges, and then it's fine, for one range. Like it might be fine from like -20 to -40, but then from -40 to like -50, it might have some weird, I don't know. I've seen this type of stuff. I'm trying to think of like a good resource to reference this. I think it was when Zen 4 first launched. I want to say, I think it was Steve from Gamers Nexus. Someone was doing LN2, and they had like the two guys from the team that worked on Ryzen as guests, and they were talking about this type of thing as well. So I can't remember the exact numbers, but this has been talked about in the XOC community. You know, like certain extremely low temperatures, the processors can act kind of flaky sometimes. So you have to be kind of vigilant on watching out for those sort of pitfalls that could exist there while trying to go for extreme overclock. But, you know, for our intensive purposes, the overheating signal, that's basically like 115C, and then after that, it's just going to turn off. So that's kind of the other two parameters there. So those are lesser known parameters. I don't think that there's a way to adjust. As far as I know, I don't think there's a way to change this value, nor would I suggest modifying this value unless you want to make this value go down. Like, for instance, if you want to drop this to like 105 or 100. But I would not recommend doing that either because, you know, if you're trying to squeeze as much performance as possible, if you're trying to run this thing close to 100C, you don't really want it to be potentially shutting off if you're messing with the overheating number. So I'll just kind of leave that as is. Assuming the BIOS even exposes that as a configurable parameter. It probably doesn't. Let's see, what else do I want to talk about? I guess we could talk about Curve Optimizer. So, I'm trying to think, is there anything else? Is there any other, like, key definitions that we need to be aware of? I don't think so. I think that's kind of it. So, the other tool, this is probably one of the most useful tools that exist within the realm of the Precision Boost Overdrive, is something called Curve Optimizer. Can't spell today. Curve Optimizer. So Curve Optimizer, so every processor, every CPU, this is just in general, has something called a frequency curve. It looks something like this, where essentially for a given voltage, well, I guess we'll say down here, we'll say this is the voltage and this is the frequency. For any, oh, you guys can't even see the voltage because I'm blocking it. I guess, should I move this up here? Let's just move this up here. We don't need this up anymore. So yeah. So for any given frequency, so for example, if I label up here 6 gigahertz, this is 6 gigahertz, and then for any given voltage on this voltage curve, as I increase voltage, so as voltage increases going to the right, you can get higher frequencies. However, at a certain point, it'll become, I guess, what's the word? Unfeasible to continuously trying to raise voltage to get more frequency. So in the beginning, it scales really, really well. So for a, you know, like I guess for every 0.01 millivolt or whatever, or microvolt, you know, like you might get 100 megahertz of frequency. Then it starts becoming like 25 megahertz of frequency, and then you're basically grasping for straws at certain megahertz, usually like 25 megahertz chunks or 15 megahertz chunks at that point. So you get 40,000 plus just using Curve Optimizer, and I've hit over 43,000. Oh, that's really interesting. Yeah, I really need to look into that more then. But you're probably using a really good liquid cooler. You're probably using like a 360 radiator or something better than that. Or maybe like a fully custom loop, which is probably what I would need to do, like if I wanted to really show off like actual use case with Curve Optimizer. Because with me, you know, the Noctua NHD15 is nice, but it doesn't really allow me to do a whole lot with this. I mean, unless I won the Silicon Lottery and my CPU is really, really good with a given voltage at a higher frequency. You know, but you never know, right? It's basically Silicon Lottery at that point. Custom loop and a really good CPU. Yeah, you got a really good one. 43,000 on Cinebench R23. That's very good. That's very good. Um, so, but you guys kind of get how this works, right? Like, as you want to go higher frequency, but it's going to require higher voltage. So this is why at the beginning of the stream I was talking about undervolting, because a lot of people have asked me about undervolting from, especially on the Intel side, because Intel is extremely hard to maintain the temperatures. But when you undervolt, you do get much better temperatures. But that applies for both of them. Yeah, that is fast. 43,000 is really good. But you can see, like, the thing about the frequency, the curve optimizer, or the frequency curve itself, it usually levels off. So it's almost like over time, it's like it becomes a really, really flat line there, where it's really hard to get higher frequency, to the point where you become limited by the two things, the process node and the silicon, and how it actually works. So and the only way to see those limits is to go under LN2. Like that's where the extreme overclocking comes into play, because then you start playing with shutting off certain cores, maybe turning off like running less cores per CCD and that sort of thing to try to get the world records for. But at that point you're no longer running the CPU as a full 7950X. But there's different categories for overclocking, right? There's like single core overclock, the all-core. I personally think the all-core one's the most interesting one for each CPU, because that kind of shows you the limit of what the CPU truly can do with all the cores active. Core 0 through 7, negative 30, and 8 through 15, negative 20. Oh, that's interesting. So you got one CCD. One CCD is better than the other. And you know what? I remember reading, like the first few days, I was reading a lot of, I was reading up on it, and a lot of people were saying how like one CCD seems to clock better than another CCD. You get more consistent higher scores on Cinebench with the 13900K. Yeah. Yeah, and the reason why that is because the 13900K has all those extra E-cores. The E-cores help. The E-cores do actually help when it comes to multi-thread, especially because they clock much higher than the Alder Lake ones. That's the real reason why. I mean, not only do they clock much higher, but there's more of them. There's like double. There's double across the board. So you get more. Yeah, CCD2 is always going to be slower than CCD1. Okay. Yeah, that's what I remember hearing. So the only other thing that I want to talk about here, so that's curve optimizer, but that's definitely worth digging into. The only thing about curve optimizer, though, that I do want to touch on, as far as I know, is curve optimizer, because all of this is considered overclocking. Curve optimizer is part of the performance boost overdrive. But when you're using curve optimizer, typically what you're trying to do is you're trying to fine-tune the amount of gigahertz. Like, for example, for any point, for any type of given frequency, like, for example, if this is 5.8 gigahertz, I want to try to see if I can do this at stock. Like, let's say if this is the stock curve means that for 5.8, I need this amount of voltage. Whatever that number may be, right? Because it's different for every CPU. It's all based on the silicon lottery. Every CPU has its own frequency curve, or frequency to voltage curve. They're all different. Now, what Curve Optimizer is doing, Curve Optimizer is essentially saying, if I apply a negative or positive voltage offset, if I apply a negative, so like what Joey just said in the chat, negative 30 and negative 20. So negative 30 for CCD0 or CCD1 and negative 20 for CCD2. What that is basically saying is, for a given frequency, give me that frequency at possibly a lower number. So essentially, where this intersects here, I want this same frequency, but now at a lower voltage. I know I didn't draw it out that well, but essentially it changes the shape of the curve. That's effectively what's going on here. It's changing the shape of the curve. Curve optimizer is tuning or optimizing the curve. It equates to a lower voltage and a lower... Yes. Well, the temperature equates... Well, the temperature isn't what you're tuning. The temperature is just a byproduct. The lower temperature is a byproduct of using a lower voltage. Now, having said all that, you can go the other way. You can put a positive offset. So if we do a positive offset, now, you know, what you're saying is I want that frequency, but because I'm doing a positive offset, we're going to have higher voltage, which means now it's going to look probably something like this. It's probably going to look something like that, which means where it intersects now, you know, it's... Let me go back to the black color here. So now it's like the same frequency, but at a higher voltage. So the red is positive offset. I think it's called offset. Blue is negative offset. So you can go both ways. But like Joy was saying, if you put a positive offset, the byproduct of running a higher voltage for a given frequency means that you're going to run the CPU hotter. It's going to generate more heat than stock. So typically, negative offset is the way to go if you're trying to optimize the system for less power, less heat, less noise, while trying to obtain the same frequency. Typically, you're not going to be able to get better frequency when you're doing a negative offset, because negative offset on curve optimizer is basically undervolting the CPU. You're basically telling the CPU, give me 5.8 at, you know, a voltage less than stock. And that may not always work for everybody. So that depends on the quality of the silicon. So that is where the whole what I want to say, that's where the silicon lottery comes into play. It is not undervolting the CPU. Well, it is limiting the amount of voltage that the CPU can pull for that given frequency. So it is kind of limiting the amount of power or the amount of voltage that you can draw. Because you're saying, with the curve optimizer, you're saying negative 30 is like a negative offset. So it's basically saying, try to hit that frequency with a lower voltage number. So that's kind of like undervolting. Now, it's not a manual undervolt, but it's essentially automating the process. It's trying to search for the voltage number that the CPU can use, a lower voltage number than stock, to be able to hit that same frequency. Now, if it's not able to do that, it's going to be unstable, or it's just not going to work, right? That's why people punch in like negative 30 and then the CPU's unstable. So it's kind of like undervolting in a way. But what it's doing, it's a little bit more intelligent than that, because it's basically figuring out the value, the actual voltage value for that given frequency based off of the original curve optimizer. But then when you're putting that negative number in there, it's actually like changing the shape of that curve. Right. That's where it makes sense. It makes sense if you have a really good binned processor. So your mileage may vary there. So that's why I want to mention that, though, because it's not like everybody can just go out, buy a 7950X and you know, do the same thing. Like, not everybody can go in and do negative 30 on CCD1 and negative 20 on CCD2 and expect it to be 100% stable and use the exact same lower amount of power, right? Like, someone might have a CPU that's not as good, silicon-wise, so they might only be able to do -15 or -10. You know, like they might not be stable at -30. So it is kind of like undervolting. You had to go through, yeah. See, and that's the binning process. So this is something that I think it's definitely worth looking into. Like if people watching this video, if you guys have the Ryzen 7000 CPUs, you can play around with this. Just know that your mileage may vary. So there is going to be a lot of trial and error. You might be able to set it to -30 and it runs fine, but then you put it to sleep and you wake it up and then it's unstable after it comes back. You know, those sort of things. I've seen that happen, or I've heard reports of that happening. So you might have to back it down to -15. What I would do is, a lot of people like to try to work their way up. I try to rule out things that are more likely to fail early on. So I'll probably try like -30 first, and if it doesn't work, then I'll do like -20 and then -15 if that doesn't work. So I always try to see like what's the upper limit I can get right off the bat. But yeah, that's -30 is really good. If you can do -15, I think that's kind of average. If you can't do -15, then you basically lost the silicon lottery. If you get -15, that's pretty average. From what I've seen online, I've seen a lot of people have success with -15. -30 is extremely good though. So -20 is also decent. -25 is really good. But -30 is exceptional. So people might ask, well, what's the point of positive offset if it generates more heat and uses more power? Well, extreme overclock is the answer. So you won't really see positive offset for everyday normal use. That's typically only going to be used in the realm of extreme overclock. So think LN2, chillers, definitely full exotic custom loop, that sort of thing at the very minimum. But even then, just because of the way the TDP and the power draw and all that stuff works on Zen 4, positive offset, in my mind, is really reserved for extreme overclocking setups. People that are going for like world records and that sort of thing. So that's not really I'll say, it's not really the average type of use case there. So definitely a negative offset is the one for optimizing the system. So that's going to be Curve Optimizer. Hopefully this kind of illustrates the concept. The last thing I do want to talk about briefly is OC mode, or the manual overclocking mode. So this is kind of a carryover from the early days of Zen 1. So OC mode. So this is kind of my second topic that I wanted to discuss here. So I did say that PBO is precision. Did I say performance boost? Precision boost overdrive is essentially the primary way that you're going to overclock these CPUs. Hey Joey, super chat. Thanks for the super chat, man. Much appreciated. So the PBO, precision boost overdrive, is really where most of the value from the overclocking is going to come from. So the other option is going to be the OC mode. OC mode is, think of it like manual overclocking, very granular. Essentially, you can dial in a static vCore, and then that's basically what it's going to run 24/7. So that's not really that great. That's just kind of there to test what you can do with the processor in terms of trying to tune it for a all-core frequency workload. Realistically, I don't really recommend using the OC mode. It's kind of there, like from the default. If you go into the advanced BIOS settings, it's usually the first thing you'll see is the OC mode. All the precision boost overdrive stuff is hidden away in the advanced section, typically under like either the AMD common BIOS settings or the CBS settings, or something along those lines. Whereas the OC mode is typically going to be AI Tweaker if you're on ASUS, or Gigabyte just kind of has it right there on the front page, and etc. Manual overclocking was how I got greater than. Okay. Yeah. That's actually really good to know. So you did manual overclocking. That's interesting. Because the way I understand it, as soon as you do over OC mode, you lose out on a lot of the boost behavior with precision boost. So as soon as you start doing anything with OC mode, you can't use stuff like curve optimizer. You can't change things like PPT and EDC. All that stuff just kind of goes out the window when we're talking about OC mode, because it's kind of a legacy mode that was carried over from Zen 1. I remember when Zen 1 first launched back in 2017, and I remember I wanted to overclock the processor, and the only way that I could do it at launch was through OC mode, unless you had either a Crosshair Hero, which I got at a certain point later on, which exposed what they call the P states, the performance states, or I guess power states, P state overclocking on Zen 1. P state overclocking essentially evolved into what we have now with precision boost overdrive. Back in the days of Zen 1, if you wanted to overclock Ryzen, your only option was either OC mode or you had to do what's called P-state overclocking. Today, we don't really have P-state overclocking anymore. Now it's really all automated. It's all PBO based. And you have curve optimizer and those other tools like we talked about with the PPT, the EDC. But with OC mode is really for world record. OC mode is really going to be for like people who are trying to go for world records, people that are probably going to be doing LN2. It's a legacy method at best, and you're really not going to do a whole lot with it if you want the benefits of the power efficiency. If you want the C states to downclock the processor when it's idling, you're definitely not going to want to use OC mode. As far as I know, OC mode will turn off, not only does it disable curve optimizer, PBO, all that stuff, but it also, as far as I remember, it disables things like C states. So Windows won't downregulate, or it won't downclock your processor when idling, and that just means you're just going to be sitting there with a processor that's just using so much electricity unnecessarily, right? Unless you're actually doing something with it. So again, OC mode, it's kind of there, so I do want to touch on it briefly here at the end, just because it is something that you should be aware of if you are looking at overclocking, even if you're like a beginner, like you're new to overclocking in general. And I know it can sound like a very daunting task. There's a lot of acronyms here that are kind of all over this the whiteboard here. A lot of stuff to keep track of, like power, thermal, voltage, the different methods, the different tools that exist within PBO, or they don't exist if you're using OC mode. But even then with OC mode, you still need to know like vCore, and maybe some other things like SoC voltage might be a thing that you need to be aware of, and that sort of stuff. So overall, that's kind of a quick fundamental 101 on how to overclock Zen 4. And a lot of this does apply to Zen 3 as well. So if you guys do have an older, like an AM4 based Ryzen 3000 series or 5000 series processor, as long as it's not the 5800X3D, because that doesn't support overclocking. But you know, all these other Zen 2 and Zen 3 processors essentially use the same concept here. It all applies. The only thing that's different is the memory, of course. So we did talk about DDR5 earlier, because DDR5 does have some newer terminology, you know, like the U clock and the mem clock, although that was there in Zen 3, and F clock and that stuff all did kind of play a role in it. So Infinity Fabric, those are all kind of the same concept. So a lot of it does apply to the older CPUs as well. It's not like all of this is brand new, never before seen stuff. So it's all been there for many years now. But that's really interesting to know that OC mode is what allowed you to get 43,000 on Cinebench. You know, I might actually try playing around with that. But see, I don't have the cooling. I just don't have the cooling system in place to be able to even try to get those type of numbers. But I might play around with curve optimizer again, just to see like if my CPU, how well of a bin to CPU I have. So I don't know. I was actually kind of tempted to get one of those Micro Center deals for like it was like 248 for the 7600X. I was thinking of getting like a 7600X with a cheap B650 because they give you like a DDR, they give you free DDR5 if you buy a Ryzen 7000 processor from Micro Center. So I was thinking of getting the Ryzen 5 just so I could play around with the overclocking, because that CPU should be much easier to overclock since it's a single CCD, you know, less heat, less power. So I was thinking maybe I might be able to do something with that on an air cooler. But, you know, I went over to Micro Center on Friday, Black Friday, and man, it was so crowded. It was so crowded. I just went in. I was there for probably like 2 minutes just walking around the store, but there was too many people in there. I just turned around and left. I gave up. I gave up. I was like, yeah, I'll just keep my $250. That's pretty much what I had to talk about on this stream. Like I said, next year I plan to probably try to update my test system. Well, you know what? I might be able to do some of this content with the older Zen 3. The test rig that I have right now, you know, that has a 5800X, so I could probably illustrate some of this with that one. And that's on an Asus Crosshair 8 Hero board, so... Yeah. You know, it's weird. Like, I didn't think... Well, I kind of thought that there'd be a lot of people there. But the interesting thing about Micro Center... So, let me see. Let's kind of pivot here a little bit. Let me go back to Micro Center. Micro Center had some really interesting deals. I think we talked about this last stream. Here, let me bring back up the web browser. There we go. So they had some interesting deals for Intel, and then they had some... If someone was looking for a really, really cheap Christmas gift type PC, you know, for something like $130 for this, the Matisse, so this is Zen 2. It's kind of old now, but, you know, $130 for basically the processor and the motherboard. And that's a 6-core 12-thread processor. That's still pretty good. But this is the stuff that was interesting to me. Like, I was really tempted to get this, the Raphael, the 7600X, because, you know, I was thinking, you know, I could update my test rig to this, and then I could use this for overclocking. Because I do think that this is probably easy to overclock compared to the dual CCDs. But, yeah, it was just too crowded. It was way too crowded. There was lines and lines of people. There was basically a line of people all the way around the store for checkout. And then there was another line of people. Like there was like an outer ring of people all around the store, like inside the store, to check out. Then there was an inner ring of people all lined up for the build your own PC section, all waiting to either buy, you know, an Intel or an AMD based CPU and motherboard combo. Because I think what really got people to go into the store were these bundles. So not only did the Intel, they had like the doorbuster. The doorbuster was kind of like this 129 for this 6-core 12-thread with a free motherboard. And then basically a lot of these were pretty tempting too, because you get free 32 gigabytes of DDR5 6000. DDR5 6000 is really good RAM. You know, this one in particular, the 7700X, I think this was a pretty tempting offer. But then even Intel had some pretty good ones too. So the Rocket Lake. The interesting thing about the Dallas Micro Center was they finally leave it to Black Friday for Micro Center to finally offload all their 11th gen Intel i7s, because they could not for the life of them get rid of these processors. However, there were so many people in the store that they were able to offload all of their, I guess, the Asus Z590 and all their 11700K, because they're finally sold out of 11700Ks. You know, for several times this year, I was tempted to buy one of these because I kind of wanted to look at 11th gen. You know, I'm the type of person that when people say a product is a waste of sand or a waste of effort and it should not exist, I'm the type of person that wants to actually buy it. Like, that's a sort of reverse psychology that I don't know why it works on me that way. But like when reviewers were basically saying that Rocket Lake, Intel's 11th gen, was trash, it was a waste of silicon, they should have never made it, they should have never released it, that all the more made me want to actually get one. That I'm kind of like Buildzoid in the sense where he likes when GPUs consume copious amounts of electricity. I like when reviewers say that processors are trash. That actually makes me actually want to buy the processor even more. I don't care if it's worse than 12th gen. That's the whole point. Like, that's why I'm more interested in it, because it becomes like a trophy. It becomes like here, look, my 11th gen. It's such garbage. I could put it on my wall, Hall of Fame of like rare products that no one ever uses. You know, that's kind of the way I see it. But you know, a lot of people bought it. It's sold out, at least in the Dallas Micro Center. I was shocked because I logged in to check today, and there was literally one 11700K left in stock. And I was thinking, man, is it gonna last? Is it gonna be there tomorrow? And nope, it's gone. They sold all their i7 11th gen. So enough people were there to buy them, so they're gone. You know, $300 for that. Your mom got you the 6800 XT Taichi. They sold out now. Yeah, those are going quick. We talked about that the other day, right? Like the RX 6800 XT. Those are gone, man. Oh wait, no, they're still in. They're still in. Oh no, they're not. Back order. They're gone. They're gone. Because this was the best deal. I think, like, when we talked about this, I had a friend recently who asked me, he was looking at deals on GPUs, and he was looking for RTX 30 series, and I was telling him, you're doing it wrong. Like, if you're looking at RTX 30 series, and you're looking for a Black Friday deal, there aren't any. There just aren't any. But if you're open to getting Team Red, like, there's a ton of good deals. You even get the 2 free games. Like, you can't get this with the NVIDIA stuff. Not only is this way cheaper, but you're getting like the 2 free games, regardless of whether you're gonna play them or not. Who cares? It's like free stuff. It's $120 worth of games it's just giving you right there. So that's, to me, that's a deal. If it was me, this is the one that I would get. So congrats on that. That's like an excellent GPU. They'll be back in a few days. We'll see. Maybe. Yeah, most likely they will. Because as far as we know, AMD has not stopped manufacturing these yet. Well, I think they have stopped manufacturing them. They do have inventory to sell through. So, like, the AIB partners have already purchased these dies from AMD, so they're basically sticking them on coolers. But they're gonna be gone, like, soon. Because if you guys think about it, RTX 3080 Ti, 3090, and 3090 Ti are all basically gone. So AMD is in the same boat, where soon their high-end offerings are going to be gone too. Like, even this, like the Taichi. Oh, you got the Taichi. Yeah, the Taichi one. Yes, you're right. Yeah, so this is the one, and it's auto-notify. So this one might not be back. So we'll see. I don't know, but I can tell you guys, like, AMD's not making any more of these because they gotta pay TSMC for manufacturing the actual die. So they've moved on. Like, everything now that's being manufactured is all RDNA 3. Now, we won't see the smaller Navi 30, what is it? Whatever the RDNA 3 cut down, like the 7800X, the 7700X, the 70 or XT. I keep saying, oh man, the 7800 XT, the 7600 XT, the 7700 XT. Those GPUs aren't going to show up until well into next year. So if I had to guess, I would say March. February, March is when you can expect the 7800 XT. And then probably April, May, well, probably June. Probably June will be the 7700 XT, or maybe the 7600 XT. We'll see. Expect AMD's RDNA 3 GPUs to slowly roll out throughout the course of next year. The same thing with RTX 40 series. NVIDIA's more affordable offerings will show up next year. But, you know, they're not going to sell them until they can get rid of more of their 30 series. The USB-C. Oh, you know how I am about USB-C on graphics cards. Yeah, this is kind of like the reference card because it's got that USB-C port. Did the other one have that? Oh no, see, like this one has the 3 display ports. So, yeah. Yeah, that'll probably be a while from now. If there is going to be a 7950 XTX, it's probably going to be a year from now. Or at the earliest, it would probably be late summer next year. I don't foresee that coming soon. Think of it like this. Think of it like how NVIDIA does the TI. So typically, NVIDIA will launch the TI at least a year. Well, okay, not always. But, okay, remember the 1080 and the 1080 Ti. The 1080 was May 2016. The 1080 Ti was March 2017. So the 1080 Ti was almost a year after the 1080. So like I was saying, if you think about it that way, the 3080, the 3090, and the 3090 Ti were very similar. So the 3090 was what? Not September. That was the 3080. What was it? October? October 2020 was the 3090. And then the 3090 Ti was end of February this year or March of this year or somewhere around there. It was like a long time. It was way more than a year apart. So, how much did 6800 XT? 6800 XT's MSRP was $650. But last year it was like $1,200 or $1,300 or even $1,500 because of the crypto and Ethereum and all that stuff. So yeah, the price of it last year was really, really high. Yes. Yeah, the 3090 Ti. Yes. So 3090 Ti is going to be more reliable than 3090. 3090 is going to be one of those cards that NVIDIA is going to wish they never really made the way they did it, because I have a feeling that the 3090, that card in particular, is going to have a lot more RMAs than the other 30 series cards. And that's because the memory on the back usually cooks itself to death over a long period of time. And remember, they had a bunch of issues with 3090s dying when New World launched. What pins do the 6800 XT need? Dual 8-pin. You need dual 8-pin. Without even looking, I can already tell you. But I'll look. Oh, I'll take that back. Triple 8-pin. You need triple 8-pin for the Tai Chi. The Phantom is dual. The Tai Chi is triple. You can see it. Like right here above me. There's 3 8-pins on there. So you need 3 8-pins for this. Right there. There's another view of it. So that's like a 4080 then. It has 16 gigabytes of memory, and it has triple 8-pin. That's essentially what a 4080 is. What are you asking? What pins do the... Yeah, we looked at it. So it's those three. Yeah, that's... Yeah. 3090 will have issues with the VRAM cooking the GPU. Or they'll cook themselves and they'll die over time. The way it will play out is... people who don't know that much about technology, but they bought a 3090 because they think it was good or whatever reason. They just spent, a lot of money on a GPU for whatever reason, just to play games, which is kind of weird, but people do that. And they don't know much about the technology. They just buy it because, someone told them that it's good or whatever. What will happen is the graphics card, as the GPU memory on the back of the PCB goes bad, it turns into artifacting. It starts off with artifacting. They'll be playing a game, and then all of a sudden, they'll start seeing, either white specks, white spots, and it might be really subtle at first, a few of them. Then all of a sudden, it's kind of, all over the place. Then they'll see weird triangle banding that doesn't look right as they pan the camera around in the game. That's a sign that the memory is defective. So if you have a Founders Edition 3090, you should replace the thermal pads on the memory. I mean, I guess, yeah. I've heard that helps. Thankfully, I dodged the bullet on that one. So I don't have that GPU, so I don't have to worry about the memory cooking itself. Where should you buy a 888 pin? It has nothing to do with the 888 pin. It depends on the power supply. You have to have a power supply that has 3 8 pins. I've covered that on my channel. I have a review video of an MSI Meg AI 1300p, but you can get an MPG 850 watt, and that'll be fine. Yeah, it has nothing to do. You can't just buy an 8 pin. You gotta. It's the power supply. Someone just commented on my MSI video too. I just saw the comment. They write, I've got a 4090 sitting here for a month and haven't been able to use it because of this stupid PSU is nowhere to be found. Man, they should just use the adapter. Just use the adapter that comes with the 4090. And pray that it doesn't burn down your card in your house or something. What's on your... Oh, yeah. Will the Corsair be good? No, look, it depends on... Here, look. MSI MPG... what was the number? This one. Here's one. And this one's got the special power cable. This one's got the special power cable. So, it's got... Oh, this one might not have enough. Oh, no, this one will have to have that cable from the 12 pin. Or you'll need to use a 16 pin to splitter. It's got it on here. I think it does. Yeah, so this one. So you guys, you can't really see it here, or actually look. So check this out. This cable, you guys can see the mouse. This cable that I'm circling, this is that very high power cable, the 12 volt on one end. This connects into the power supply, so that will connect right here. But that cable, specifically this one, on one end it has the 16 pin to the power supply. On the other end it has dual 8 pin. So you'll need this cable. Well, you don't need this cable, but if you wanted to use this power supply with that graphics card, you would have that cable connecting over here, and then that would give you 2 8 pins to the graphics card. Then you'll need to use another separate 8 pin up here for the third one, and then you still have the 2, or 1 or 2, whatever, for the power supply, or the EPS 12 volt to the motherboard. So that's something to be aware of. So this power supply would work. So here's some customer images. Oh, I don't know what happened there. That doesn't look good. I don't know what happened. Did they mess that up, or was it faulty from the factory? That doesn't look good though. But this one will do what you need it to do. And the reason why I'm recommending this one is because it does have that newer cable type. So, like, for instance, if you were hypothetically going to use a newer graphics card that had, like, in the future, right? Like, not today, but in the future, like years from now, this power supply would be able to support a graphics card that would make use of that single 16-pin. So yeah, that's one way to do it. So this one, I encourage you, go check out that video on my YouTube channel that I did. I think it was almost a week ago now, on the power supply, because I have a content covering the power supply cables on the channel. Oh, the RM850, that's a bundle. Yeah, that has a that's a liquid cooler for the CPU. What were you buying again with the CPU? Why are you getting a CPU cooler? Oh yeah, oh, I remember now. Yeah, I remember. We were looking at the full. Yeah, was this the one, or was this? I'm trying to remember what we did. Like, I vaguely remember we were looking at the build your own PC part picker. We were doing this, and I went through that whole exercise and came up with these parts. Oh, but you went with the Tai Chi. But yeah, this was kind of what I came up with as what I would do if I was building a gaming PC. I still might end up getting this sometime next year. Like, this might be a preview for content well into the future. The only difference is, instead of this processor, it'll most likely be the X3D CPU from AMD is the one I'll be pairing with probably this motherboard. And I already have this RAM. Well, okay, not this specific one, but I have free RAM from Micro Center just sitting around, not being used. Should you get AMD or Intel CPU? What works better with the RX card? AMD CPUs have better SAM performance with an AMD. Yeah, since you're building an entirely new PC, definitely get the Ryzen 7000 series processor. I would recommend this processor, or maybe like even the 7600X to save some money. But you never told me the budget. Now, you already bought the GPU, but you never told me like what's the maximum amount of money that you're going to spend, because that kind of determines what we can recommend here. But regardless of what that number is, I would still recommend the new AMD Ryzen 7000. I'll put it another way. A year from now, or maybe 2 years from now, well, okay, we'll just say 2 years from now. 2 years from now, the motherboard that you buy today for AMD will still be more relevant than the motherboard that you could buy, any motherboard you could buy today for Intel. And that's the reason why I would recommend AMD. I'm not recommending AMD because of the processor, even though it's basically the same performance as the Intel 13th gen. I'm recommending it because of the platform. The AMD platform is far superior to the Intel platform. I have numerous live streams on this topic alone. I have a video talking about, like a separate YouTube video doing a deep dive on B650E and X670E, and why I would recommend those over the non-E version or any of the Intel ones. So the AMD one's better overall. Let me put it another way. We're talking power efficiency. Wait, if you're doing anything like streaming, rendering, whatever, anything where you need to load up the cores, the AMD one is going to be better because it's going to use less electricity. And if you're doing something, like for example, you guys may see that sometimes I do really long live streams like this. If I were to stream on the Intel 13th gen, it would get uncomfortably warm in my room. And that's because that CPU is dumping nearly 300 watts of waste heat while streaming to YouTube. Now, that is one of the reasons why I am streaming to you guys. I choose to use the new AMD Ryzen 9 CPU. This is the reason why. This is one of the reasons why. It's one of the most, I guess, practical reasons why I use the Ryzen CPU to stream as opposed to the Intel one. Because I could just as easily stream to YouTube to you guys on the Intel Core i9 13th gen. I have both of them right here. So it's not like I can pick and choose whichever one I want. But this one is far more energy efficient anytime I'm doing things that load up all the cores, and I'm going to be doing that for an extended period of time, meaning more than like 2 hours. We've been live for almost 2.5 hours now, and it's totally fine in this room. I'm not like sweating or anything. There's not a lot of waste heat coming out of the processor. The computer's quiet. You know, everything's fine. So that's why I would push you in that direction on a practical standpoint, but more so on a future-proof standpoint. The platform, the AM5 platform, is far more future-proof than what you can get on Intel today. When we looked at Intel's offerings, their motherboards at launch, I concluded that if you were going to buy Intel, you have to buy last year's motherboard, which is Z690, because that one makes more sense financially, and they don't do these weird shenanigans where they peel off lanes from your graphics card slot to give you M.2 drives that can support Gen 5 speeds. So that's the reason why I would definitely recommend AMD. There's like a lot of reasons why I would recommend AMD, but those are just a couple of them. The efficiency, the platform itself, the longevity, you know, the socket, you could just drop in, upgrade later, like 2 years from now, 3 years from now, whatever. You know, like people might ask, well, what if I keep my computer for 5 years? Well, think of it this way. Think if you're me. You have both of these. 5 years from now, this CPU is dead. Well, I can't upgrade it. It is fixed. The motherboard and the CPU are bound day one forever. Like a marriage. You can't get rid of it. This one, if I want to upgrade 5 years from now, even after like AM5 is replaced by AM6, I can still buy a newer, better processor than this 5 years in the future. Whatever the last AM5 processor happens to be 5 years from now, I can drop that in this exact same motherboard via a BIOS update, and that's going to be it. So it's like, to me, it's a no-brainer. Like, if I had to choose one, I would just pick this and be done with it. So I don't know, like, why there's so much vacillating around, like, choosing one over the other. But that's just me. Just say 750X since Ryzen 9 can be any CPU. Wait, you want to stream, so you might get the AMD. The 7900X will not help much over the 7700X for streaming. It can, but if you're doing X264, it definitely will. But nowadays people, yeah, I would say it still is going to be better. But the thing is, I mean, before I had the processor I have now, I was streaming on a 5800X, which is an 8-core 16 thread. I never had any problems with it. So, I mean, you know, that's somewhat accurate, but I would kind of say that the Ryzen 9 would definitely be better suited for streaming overall. Yeah, like Joey's saying, the 7900X is a great CPU. Yeah, for 12-core, 24-thread, yeah, that's kind of an all-rounder. The way I see it is the 7900X is often overlooked, but I feel like that's the best all-rounder. Kind of like how the 13700K from Intel is currently the best all-rounder. I do think the 7900X is the best all-rounder on AM5. Now, it is pricier than the 13700K, but overall, you're getting a much better platform longevity-wise. So in that point, in that regard, even though it's roughly $100 more than the i7, if you're going by the current prices, I do think that one's still, to me, that extra $100 for like the future-proof alone is better. So, or you could just look at the other way around, or you could just buy, you know, a cheaper processor like a Ryzen 7 7700X, get that, and then do a drop-in upgrade in the future to like a, you know, like a Zen 5 CPU, and keep the same motherboard. So there's two ways to look. There's more than one way to look at it. The thing with AMD is there's so many options that you just kind of have to make a decision and just go with one of them, because you'll never really have like buyer's remorse if you buy AMD, because there's too many options. There's too many options to evaluate, to the point where by the time you buy a processor, you already know like there's another one that you'll be able to use a couple of years from now as a drop-in upgrade. So there's no reason to kind of like second guess your decision on the processor. Just make sure like it has the right core count for the use case. So like if we're talking gaming, 8-core to me is kind of really the sweet spot. 6-core is even enough also because it's 12 thread. But 8-core is just overall better. And then anything above that, you're talking about like very specific use cases. So if you're looking at a Ryzen 9, then you kind of have to justify those extra cores at extra cost, because if you're just playing games, even if you say you're going to stream, you know, like, what does that mean? Like when people say they're going to do streaming, like, what does that mean? Does that mean you're going to have 100,000 people watching you? You know, what does it actually mean? You say you're going to stream. Are you just going to stream to your friends on Discord? Because if that's the case, even the cheapest Ryzen 5 is enough to do that. And that's going to have no problems doing that. So when people say, I want to stream, you know, what does that mean? Like, to me, that's so open-ended. That's such a generic, oh, you want to stream to Twitch? Okay, well, I mean, yeah, the Ryzen 7 will do that. The Ryzen 5 will also do that. So, you guys got to remember that years ago, back when the best mainstream desktop CPU only had 4 cores and 8 threads, people were streaming to Twitch on quad-core CPUs, like Intel i7 CPUs back in the day. And if they were running a very high-end system, that was a 6-core, 12-thread Intel socket, what was that? LGA 2011 socket X79 and then X99 later on. But that was kind of the pinnacle back then. 6-core, 12-thread was the pinnacle for streaming. And what is a 6-core today? Well, that would be a Ryzen 5 7600X, the cheapest offering. So you're going to stream to Twitch. Okay. Well, I mean, okay. I mean, any of these CPUs will be able to do that. I'm just letting you know. Like, you can spend a whole bunch of money to basically do the same thing, or you can save a bunch of money to basically do the same thing. So what the extra cores do, what the extra cores really benefit you on is the multi-threaded performance. So basically, if you're going to actually do content creation, then the Ryzen 9 CPUs really shine. But for streaming, like, you know, any of them are fine. The 12400 for $150 is a good 6-core 12-thread budget CPU. Yeah, but it's kind of old though, right? Like, I don't like to recommend the last year's stuff for a new build, unless the budget has a limit in terms of the spending. I would tend to go for something that is relevant this year, not something that's from last year. Well, I mean, the 12400 was probably earlier this year, but you get what I'm saying. 12th gen is not really new anymore. So that's why I would not really recommend that. I would probably go with, well, let's remove this. I would go with, well, I don't know the budget, but I mean, I would say, you know, like this, 235 for a processor that can basically do what you want. You want to play games. This thing beats the 12900K in gaming. Not in every game, but in, like, it's pretty much the same performance, and it's way cheaper, so it's like half the price. Oh no, you're talking about you're talking about your build. I thought you were recommending to go skew the 12400. No, for what GoSkew is doing, I would definitely buy a Ryzen 7000 processor. You just need to pick one. Doesn't really matter. Just pick one of them and just get like a good air cooler or liquid cooler, whatever you want to do, and then just get a B650 motherboard or B650E motherboard. I would highly recommend the B650E. You don't have to choose the Gigabyte one if you don't want Gigabyte, but I would definitely say B650E. You really don't benefit too much from going with X670 based off of my own deep dive analysis on the differences of these motherboards. So I do kind of think B650E is really the value king in terms of longevity, because you're getting 24 lanes of PCI Gen 5, and that's going to last you for multiple CPU upgrades. So yeah, 12400. Yeah, you're talking about the small form factor. You can stream off of Arc, but remember, you cannot use AV1 yet. You cannot stream an AV1 on Arc, and one of Arc's biggest selling points was AV1, but they don't let you stream it. That's not Arc's fault. That is YouTube and Twitch. That's basically all the content providers that don't allow you to stream an AV1 right now. So the biggest selling point of Arc was the AV1. Now you can still use the GPU to encode, but it's not going to be AV1. So it won't be as efficient as it could be. But yeah, kind of like this is what I would do. Like this is what I would do if it was me. 6800 XT, you know, this power supply, although now it's out of stock, so we can't really go with that one. So we're probably gonna have to choose a different one. This one's good enough, so I would get that. And yeah, that's it. $1,800? Wait, why is it so? Oh, because of the graphics card. But the graphics card, you already got that, so we can remove that. So there. So like 1,100. Yeah, that's kind of what I was expecting. And you could go less on the SSD if you wanted. Although I kind of would go with 2 terabyte myself. But you can just go with like a 1 terabyte, like this, and that's kind of it. So there. Well, it didn't change the price much, did it? So maybe you just go with that 2 terabyte that I had up there. But that's kind of it. So you know, yeah, this is good. Now, why is this so? Like, you don't have to go with that exact cooler. You can go with, well, that Chromax is nice, but if you want to go with the Dark Rock Pro 4, I mean, that's fine too. So that's basically the same. So that's now we're at like 1,000. So you already have the SSD. Okay, we'll remove that. So that's like 951 for the memory. So wait, why is this like this? Okay, so the memory wasn't even there. So see, this is the thing. If you were near a Micro Center, you could have gotten a really nice deal. You could have gotten one of these processors with free 32 gigabytes of DDR5. But essentially, I would say I would go with 5200 myself. I would get probably this Corsair. This. Oh, man. The bots found us. The bots found us, guys. I gotta figure out how to get rid of them. What's weird is I removed the thing. Wait, hold on. Maybe I should just report it? I can put user in timeout. Okay. Yeah, I was like, what the heck? I don't know, man. I don't know why that happens. That's so random. They probably get kicked. They probably get kicked from the big streams and they trickle down into the small ones. Oh man. Well, anyway, that's kind of what I would do. Like if it was me. The reason why, again, I would steer you in the direction of B650E is I mean, two things. One, the 24 lanes of Gen 5 that go to the CPU. The other reason, though, is because with the B650E, most of the motherboards that we've looked at that are B650E, unlike B650, these include things like the postcode debug, Thunderbolt 4 headers. You can add USB 4 if you wanted to do that. But all I'm saying is that you get a lot of options. You don't have to buy this motherboard. If you want to get like a cheaper motherboard, you can certainly do that. There's a lot of options. So, you know, like there's a Prime. You can go with the Prime B650. Or you could go with M-ATX if you wanted. I personally don't want to go with M-ATX unless I'm building a small form factor. So I would probably go with that, either this. Well, that's 219. There was one that was like the Asus Prime. I think there was the Asus Prime that was up there. But there was like 160. Oh wait, 150. But that's like that's M-ATX. So probably. If we're talking like full ATX, the B650 Pro from ASRock, or the Asus, there was an Asus board. I think it was the Prime. Where is it? It was I think it was 199. No? Okay, never mind. Then it's really that ASRock. This one. So that one. That would be to keep it under 1,000. The Gigabyte Z590 is not AM5. That's an Intel motherboard. That's 11th gen. So no, I wouldn't recommend that unless you want to buy Rocket Lake, which is going to be 2 years old in a few months. Yeah, no. No. You want to look for something that's B650 or B650E or X670 or X670E. Those are the ones that work with these Ryzen CPUs. But, you know, the other thing, too, is you could also, like, if you wanted to go really, really cheap, you could go with a 5800 X3D. But I still think you're better off with long-term. If we're talking long-term, I would get this. Because I won't even talk about the AM4 because, you know, that's basically like buying 12th gen Intel or even 11th gen Intel. So, yeah, we'll kind of avoid that. It's really, if you're buying new, Zen 4, basically Ryzen 7000 is the best option. You can go 13th gen. It's just like, I just don't think that it's going to be, it's just not going to age as well. Let's put it that way. It won't age as well. That's the difference. Yeah, you have just way better upgrade options with AMD. So that's why I really don't recommend the 13th generation from Intel. Unless you're building, unless you're going to get the i5, like, none of the others really make sense. Maybe the i7 makes some sense, but compared to AM5, compared to the fact that we have decent lower prices on AM5 right now, it's kind of a no-brainer. I do think the argument in favor of 13th gen was definitely stronger a few weeks ago before these price cuts for the holiday season. But now that we have the price cuts, regardless of whether they're temporary or permanent, now is the time to make a decision. So, and with the prices the way they are right now, it makes a lot more sense. The other thing, too, is people might say, well, you can always get DDR4 on Intel. Yes, but again, that is still looking at it from a if you're okay with locking yourself into that platform, you're stuck with DDR4, and then that's basically it, and that's gonna be the computer. Like there's no drop-in upgrade. There's basically nothing from there. So it's like you're building the computer, and that's it. It is what it is, and that's all it is. So if we're talking new build, I would just go ahead and get a new DDR5 platform, and then in that regard, you can also go Intel with DDR5, but then again, the price advantage that Intel had is not really there anymore. So okay, well, I think that was kind of what I wanted to cover. We did cover all the things that I wanted to talk about, which was primarily the overclocking concepts. Let me bring that back up. So, just a review for people who are tuning in now. This stream was primarily talking about overclocking on AM5 on the new Ryzen 7000 series processors. We talked about the concepts, the different methods, the different tools that exist to do that. So the primary one being Precision Boost Overdrive. I know I said Performance Boost Overdrive, but it's Precision Boost Overdrive. It's the second generation of that. Carried over from Zen 3, but now it does work with DDR5. So there are a little bit of nuances there to be familiar with. All these different phase lock loops for the core clock, the system on chip clock, the USB, all that stuff. Now I didn't show storage, but storage is also a part of that. That's the reason why typically I don't like to mess with the external clock generator. I tend to want to keep things in synchronous mode as opposed to asynchronous mode. But if you do want to go for very high memory overclocking, then the asynchronous mode does come into play, allowing you to hit higher frequency with a slower running fabric clock, or an IMC clock in this case. So those are kind of the main topics of the stream. The ones I've outlined here in this box are the ones if you wanted to do eco mode, or if you wanted to tune those manually. So if you wanted to work with these and kind of mix that in with Curve Optimizer, you do have the ability to do that, provided the BIOS settings are there on whatever motherboard you're using. And then lastly, the other thing that we talked about was the OC mode. So this was the legacy mode that can be used to try to hit world records. But for practical use cases, I don't see a lot of people using OC mode. I personally won't really use this if I'm looking for a 24/7 everyday daily driver PC. I'm probably going to be relying on Precision Boost Overdrive and some mix of that with Curve Optimizer. So that's going to be it for this stream. Are there any other questions pertaining to AM5? I may do another video on... We'll see. We'll see. I'm waiting for newer AGESA code before I want to mess too much with diving into more overclocking stuff. At least on AMD. I may cover one for Intel as well. I might do an Intel video, or like a video on overclocking on Intel and what that looks like. Because that's not like... Basically, overclocking on Intel is more like using OC mode on AMD. Where you still get the ability of the processor to downclock at idle. You're effectively using... It's kind of like using offset volt. Well, I mean, it's not kind of it. Essentially what you're doing is using V-core and offset voltages and adjusting the power limits. Adjusting the power limits on Intel is basically like what we're doing with eco mode over here on AMD. It's just different. Intel uses different terminology from AMD, but effectively it ends up doing the same thing. So the thing that I think makes Intel a little bit more complicated is the ring bus and the E-cores can throw a wrench into things. So, but I haven't delved too much into the E-cores, like looking at what parameters are there to tune those. But maybe that is probably worth investigating in a future video. So So, all right, guys. I mean, I still see we've got concurrent viewers, but if there are no other questions, I'm probably going to go ahead and end the stream here. Hopefully, this was useful to anybody that was interested, or if you already have a Zen 4 processor and you're interested in looking at how to get more performance out of what you have with the motherboard, just the overall platform itself. But really, I think this stuff will become more valuable over time. I do think that with newer processors that you can drop into the same motherboard, or with just BIOS updates from the motherboard manufacturers and AMD, this stuff will mature and it'll just get a lot better over time. Because if anything, if it's going to be anything like how it was with Zen 1 all the way to Zen 3, yeah, Zen 1 had a lot of memory compatibility issues, but Zen 3 never had any of those memory compatibility issues. So if it's anything like that, where today, we're kind of limited to 6,000 mega transfers on Zen 4, who knows, like Zen 5, Zen 6, how those will improve the Infinity Fabric, the SoC, the IMC's quality, because I really think that that's typically what you expect with newer iterations of processors. The IMC is going to get a lot better. Because, I mean, if Intel's in the same boat, right? Like 13th gen's IMC is a lot better than 12th gen's IMC for DDR5. So I expect the Zen processors to mature in the same regards as what we were seeing on Intel. So with that said, I'm going to go ahead and end the stream. Once again, I thank everybody for tuning in and watching. And hopefully this was value in some way. And I will catch you guys in the next one. Thanks.